Okay, our next presenter is Erin Huggett. She's a chemical and research engineer from the Illinois Sustainable Technology Center.
Hey, hello, my name is Erin Huggett. I work at the Illinois Sustainable Technology Center with the Prairie Research Institute here in Champaign. And today I will be talking about using a novel designer biochar to remove per and polyfluoroalkyl substances from aqueous solutions. So I know we've been here all week, so you don't really need background information, but I did just want to quickly touch on the fact that PFAS is used commonly for their heat, water, and oil resistance. They're commonly used in clothing, food wrappers, and firefighting foam. They're called forever chemicals due to the resistance to breaking down in the environment, and that's because of the strong carbon-fluorine bonds. They're also linked to adverse health effects, both in humans and in the environment. And I wanted to note the two PFAS compounds that we're mainly going to be looking at today are the PFOA and PFOS, which you see at the top. So first, we're going to look at what is biochar. So biochar is a carbon-rich product made from biomass, such as sawdust or switchgrass. And it can actually be made from a lot of different types of biomass, and we'll actually get into that in the next slide. Biochar is different from other carbon-rich sorption products like activated carbon because we actually engineer it specifically for a purpose like sorbing a specific compound. So this biochar, for our purposes, we wanted to design a cost-effective biochar as well as an energy-efficient sorption product for specifically PFOA and PFOS. So what we did to design this product was basically we looked at a couple different variables. We looked at different biomass materials that you can use. We looked at baking under pyrolysis at different temperatures, including 650, 850, 900, and 1,000 degrees Celsius. We also looked at different additive ratios. So we are adding lime sludge into our biochar before we bake it. And so we looked at different lime sludge ratios of 20:0, 20:1, and 20:5. And then later on, we actually looked at 20:10 as well. And the reason why we used lime sludge specifically was to modify the biochar surface. So we wanted to modify the charge of the surface from negative to positive. And we wanted to do that because of the sorption occurs through electrostatic mechanisms. So here we have a bench scale sorption experiment. So basically after pyrolysis, the biochar is weighed and to calculate yield, and then it is ground and sieved and put into a small flask with a PFOA and PFOS solution in water. It's then shaken for 24 hours, and then after settling, you can take the top aliquot and prep that for the LCMS-MS analysis. So here are our first batch of results. We can see basically we just wanted to try different biomass products. So we have, cattail, reed sticks, corn, and sawdust are the ones that I'm going to be mainly pointing out. So we see that the cattails and the reed stick did promisingly well. However, those are actually foraged. So they aren't commercially available. So this would not be a cost-effective option. So then when we looked at whole corn is commercially available because we live in mid-central Illinois, it's everywhere. So we looked at whole corn and we looked at the addition to lime sludge into that whole corn biomass. We saw that the addition of the the addition of the lime sludge increased the removal efficiency. However, when we looked at the sawdust, we saw that the removal efficiency was increased quite a bit. And so we wanted to kind of investigate that a little bit more. So we looked at the sawdust 20:5 lime sludge ratio in particular. And the thing about sawdust is that in some industries, sawdust is considered a waste product. So this would be a very cost-effective option for us. So we decided to look into different temperatures. So we're using that sawdust, we're using that lime sludge, same ratio, and we decided to look at different temperatures. So we're looking at 650, 850, 900, and 1,000 degrees Celsius, both without lime sludge and with lime sludge added in. And so you can kind of see the general idea is that with the lime sludge, you can see an increased removal efficiency. So you can kind of see it in the 650, but you can really see it in the 850, 900, and 1,000 degrees biochars. With the addition of that lime sludge, the removal efficiency increased significantly. So we wanted to look in particular at our best options. So we see that the 20:5 ratio for the 850 biochar had the highest sorption and highest removal efficiency. We see the PFOA removal on the left in the blue is at 99%. The PFOS linear removal is at 99.6%. And the branched or isomer PFOS is 100% removed from that biochar. And when you compare that to the activated carbon, that's just a commercial activated carbon that we had, you can see it's actually a higher removal efficiency than the activated carbon. So we decided to move ahead with this biochar. The next thing we wanted to investigate was the lime sludge ratios. So we looked at different lime sludge ratios, including 20:0, 20:1, 20:5, and 20:10. As you can see, our best two options here are the 20:5 and 20:10 ratios. They're both better than the activated carbon, but it's pretty negligible at this point when your removal rates are so high. So we just decided to keep going with the 20:5 ratio because we see that there is a slightly higher sorption removal rate for the PFOA, but again, it's so small that it's pretty negligible at that point. So to investigate further into why the lime sludge ratio is helping, we wanted to kind of look more at what pyrolysis does to the actual lime sludge itself. So we see that on the left side, we see the lime sludge by itself without being baked is not great, pretty much under a 20% removal efficiency by itself. However, when we bake it, you see a slight increase in the removal efficiencies. So you can see the next group over is the 850 lime sludge. So it was baked at 850 under the same conditions as our biochar. The next two you see, we wanted to look at post-treatments instead of pre-treatments. And so the post-treatments include the untreated 850 biochar mixed with the not baked lime sludge. And then we have the 850 biochar mixed with the baked lime sludge next to that. And the results pretty much show that it's corresponding with the lime sludge additive that we used for those post-treatments. However, again, we see this huge removal efficiency for the pre-treatment. So we can actually see that there's a synergistic effect going on with the pre-treatment as opposed to the post-treatment. The next thing we looked into were kinetics. And so we wanted to see exactly, how quickly the PFOA and PFOS compounds were being sorbed by the different biochars. So we see the blue line on the left-hand side is the PFOA sorption for designer biochar. The orange is the untreated biochar, so just 850, no lime sludge. You can see that the QT levels basically indicate sorption nanograms per gram. And so we see that the designer biochar has a higher QT value, which indicates that it is more efficient at sorption. We see that the balance rate for the PFOA sorption comparison is roughly about the same. We can see it's about somewhere in between 3 and 4 hours. It's after that 200-minute mark, but before that 400-minute mark. And then on the right, we see the PFOS linear and isomer. And we see basically the same thing when it comes to the QT values. We see that the designer biochar has a higher QT value, and the non-treated 850 biochar has a lower QT value. However, when comparing balance rates for this one, we see that the designer biochar actually has a quicker balance rate. So it sorbs more faster than the non-treated biochar. All right, so the next thing I'm going to get into very quickly is just short chain PFAS. So we have PFBA and PFBS here. So these are just shorter chains than our PFOS and PFOA. Historically, shorter chains are harder to capture. So we wanted to kind of just test to see where our biochar was. And as you can see on the left-hand side, we have our 850 biochars with lime sludge additives. Pretty much the 20 to 0, 20 to 1, and 20 to 5 all had pretty low sorption values, slightly higher for the PFBS for our 20 to 5 lime sludge ratio. But then we looked into different additives. So we have an aluminum chloride, an iron chloride, and a magnesium chloride that were added in lieu of the lime sludge additive. And we see that the magnesium chloride didn't really do well. The aluminum chloride did okay. But then we look at the iron chloride, the 20 to 1 ratio, and we see that there's promising results with that. So to investigate this more, we would have to look into, other additives, different ratios, and that sort of thing. So that'll be coming up the pipe. Okay, so our conclusions for this study are basically that our 850 20 to 5 lime sludge ratio biochar was the best option because it had the highest sorption rate for PFOA and PFOS. This particular biochar was more energy and cost effective to make compared to the other biochars baked at higher temperatures, like our 900 and our 1000 degree biochars. The balance time for PFOA sorption is roughly 3 to 4 hours. However, the balance time for PFOS sorption for our designer biochar is roughly 1 hour compared to the non-designer biochar that was roughly 3 to 4 hours again. For future work, we're going to have to look into different additives for those short chain PFAS compounds and different ratios as well. So we've got plenty of future work coming up. We want to continue with our PFOA, PFOS studies. We want to look into isotherm experiments where we deal with varying concentrations, resorption capacity. And we also want to look into the characterization, both physical and chemical, for the properties of our biochars. So we want to see why PFOA and PFOS, adsorb to this particular biochar so well, and whereas like other chemicals or other compounds don't. So we'll be looking into that. The other thing that's coming up the pipe is we're looking at hydrothermal liquefaction treatments, and we're looking at that to regenerate PFAS-laden biochars for future sorption experiments. The last thing we're going to be looking into are column sorption studies. So basically we'll have a column and we'll just pack that full of our biochar and then pump the PFAS through and see how well the sorption occurs in that sort of instance. So finally, I'd like to thank my special thanks to everyone who has helped me on this project, which is a lot of people, and I really appreciate all of their help. So first and foremost, I'd like to thank CERTUP, the Strategic Environment Research and Development Program. They are funding our project, so I always want to make sure to give them a special shout out. Other than that, I'd like to thank my colleagues at ISTC, including Dr. Wei Zhang, John Scott, Lee Green, Sophie Cercenis, and Rosie Delgado. Without your help, I would not be here. So thank you so much.